Well, ladies and gentlemen, let us conclude this day. Another presentation from colleagues of Sberbank. Please welcome those in charge of data research, Alexey, Vasilev, and head data researcher, Martin Tamm. And ladies and gentlemen, let us remind you that you can ask questions to our audience. Just use QR code that we're showing you at the screen below. Don't hesitate to use that one. Scan the link, join, ask your questions. So, the screen goes to our guests. Good evening, dear colleagues. Can you hear me now? Yes, we can hear you now. Good. Welcome. My name is Vasilev, Alexey, Vasilev. I'm in charge of the group for recommendation system at AI Lab at Sberbank. And today, together with my colleague, Martin Tamm, we'll be telling you about our very special library to build recommendation systems that we have just released as open source. Let us begin. Well, let us imagine a data scientist who wants to create a recommendation system. What actions, what steps would he make? First, he would love to understand what is the task to solve, what he needs to do. That can be implicit or explicit recommendation, or that can be some station-based or something that is not actually a recommendation but masquerading as recommendation. Next, after selecting the problem, data scientist needs to pick an algorithm to use so that therefore, of course, the scientist needs to look at the ton of libraries and select the best one. So, what are the problems that we're facing here? As a matter of fact, various libraries represent different data formats. For example, that can be in one library, data may be presented in one format, and another library in a different format, and in the third library, third format. So, in order to compare the algorithms, the scientist would have to make data transformation and specifically write some piece of code. And in various libraries, there are different interfaces, so that you would need to read manual for every library, spending your time to do that, and after you write all of it, turns out that in order to compare the results of the algorithms, you will have to again write some metrics of your own, or export them from some sort of third-party library. I mean, a handful of problems. Imagine data scientist is so capable that he can solve all of this. Next, what's happening next? That's not the end of data scientist's troubles. When you pick an algorithm, you first, after picking an algorithm, after everything seems to be fine, you've written some sort of code. After that, you need to understand how you will be using that data. How you will be first filtering data, picking certain values to put them into algorithms. For example, you may select only values for high estimation, only high values. After that, you would need to figure out the validation strategy. So in terms of recommendation, you have more options compared to regression or classification. You can split data randomly, or you can split data globally according to time, or can you do all the same for a particular user. So within every user, you can split data for train and part for test. After you split the data, you will need to understand how you will predict the items that should be recommended to the user, because you may make predictions based on the set of all possible items, or you can take only part of items for predictions. For example, the items that are in the test. First variant is, of course, more fair, because initially you don't know. I mean, you do know what's in the test. In addition to that, one of the important things is to select metrics which you will use to compare algorithms. As a matter of fact, for recommendations, there's a variety of metrics, and there's no one particular that is considered optimal, because it all depends on the task that you're solving. In addition to that, apart from standard quality metrics, there are diversity metrics that are also important for recommendations. I mean, maybe you recommend some really good product, and everybody clicks that one, but you're not showing most of the product, and therefore your recommendation system suffers. In addition to that, even if you picked metrics, it may turn out that you have selected a metric in a library, so it may turn out that the formula for that metric, the formulas for that metrics are very diverse. We have recently published a white paper at RecSys 21 conference about this particular situation, when it turns out many researchers, not only researchers, but also developers of tools for particular metrics, can understand very diverse implementations, and those differences may be very significant. In addition to that, even when you pick an algorithm that is better according to all of the metrics that you evaluated, quality, diversity, etc., it may turn out that this particular algorithm is unapplicable because it's just too long to take, or it takes too much processing power. Therefore, another criteria for selection is applicability of the algorithm. So it turns out that data scientist is experiencing some trouble. So we need to do something about that. So one of the options there is to build some sort of framework that will, first of all, unify the data format. So you don't have to write any additional code. Besides, the development speed will be faster. You don't need to read a ton of manual for different libraries, which often have only one or two implemented algorithms. I mean, there's convenience for development. In addition, for the framework, there may be implemented a number of scenarios. In addition to primary algorithm, you may make some sort of pipeline that will execute the entire chain of computation operations. We have been thinking about that and decided to develop our very own framework to build offline recommendations. We called it RePlay. And let me hand over the floor to Jan-Martin Tamm, who will be telling about it in more detail. Jan-Martin, please. Jan-Martin. Hi, everyone. My name is Jan-Martin. I am a data scientist at the AI lab in the group of recommendations. Let me tell you briefly what is RePlay and what can it do. RePlay is an open source library written on Python with the use of PySpark and PyTorch tech. And as a modular solution, it helps to solve the tasks when we have to create, while creating recommendation systems at every stage, starting from pre-processing of data, splitting it for testing and training, then optimization of model, and of course, metrics calculation. You can find this implementation on GitHub already. RePlay uses Spark that is specifically geared up to work with big data and cluster loading, meaning that at the beginning of work you need to set up the Spark session. But what if you don't have any clusters, you have only your very own laptop, and you don't want to deal with Spark session setting? Well, for that we have a solution. If you are not sending any additional parameters, by default we create base session for you. Also, we have auxiliary function getSparkSession that helps you to create minimal configuration, while in the meantime, without getting too deep into settings. Here we create Spark session that is limited to 2 GB of RAM. And similarly, if you have your very own cluster and you know what sort of settings the Spark should have, you can send them to this state object, and all of the modules of the library will be able to use it. Next, RePlay has been implemented with a set of filters for pre-processing of data. For example, we have this toy test example of data. What can we do with it? For example, we can filter all of the records based on the rating value and leave only those records where rating is above certain threshold. Also, we can keep only the users with minimal threshold of interaction. For example, 3 interactions. Or users with 1 or 2 interactions will be deleted. You see, the logs give us a warning that we are actually throwing out too much data and maybe we want to lower the threshold. Also, we can filter data conveniently based on date. That's only part of the functions, and we can find the rest in our documentation. That is the example of how you may interact with the data. Also, we have implemented splitters, and let me show you the range of strategies presented here. The splitting data strategies. For example, you can split based on global date. You can split based on the amount of objects within users. Random splitting, splitting based on that keeps all of the records of certain users into the test, and they will be cold records. The rest will be used for training. And also we have random split of some users to training and some users to testing. We have implemented major metrics for quality of recommendations, such as heat rate, precision, DCG. Probably you know this ones. Also, we have some metrics for diversity. For example, surprisals that are showing how unpopular items from long tail are getting into your recommendations. It shows how the recommendations of your model are different compared to recommendations from a baseline simple algorithm. Also, we have coverage that shows us what is the share of items gets to the recommendations amongst all of the set of the objects that you have in the system. Also, in order to work with metrics, so that we don't have a ton of prints, we have this object that's called experiment. You can send to it the metrics to calculate all of the values k beyond the threshold and the amount of recommendations that you use to compute that, and using the add result method, you'll be able to compute all of those metrics and also display them as this neat table for values or percentages compared to certain baseline. RePlay has baseline models, popular, recommended models. We sample random gradually based on popular distribution. We have baseline models like KNN, matrix split using ALS, SLIM, neural network models like NeuroMF, and autocoder. We also have models based on associative rules that allow us to recommend for other objects that often are encountered with that object in the baskets. We also have cluster recommender that, based on the users, allows to assign them to certain cluster and recommend to them using information. Also, we have 2 wrappers for popular solutions from other libraries, implicit LightFM. Those wrappers provide convenient integration of those models into the pipeline that there is in the RePlay. And they provide conversion of data from Spark and back so that you would never have to think about that. Also, we integrated into RePlay the optimization library for Optuna parameters, and in the simplest case, you would not even need to think about the threshold for certain parameters because we have already thought about that instead of you. So you would simply need to say which data set you would be using for optimization, which metrics you optimize for, you need to define the length of the list of recommendations and how many trials you want to spend on that. Here's one point, and hyperparameters will be selected and returned. You can train model with the best parameters. However, in addition to this baseline things that are encountered in many other places, there are more complex entities that we call scenarios. Scenarios include several models working and their combination. For example, let us consider that we have some baseline model that is good. We love it. And it gives us good recommendations, but not for all of the users. And not always in the quantity that we need. For example, in this example, the first user lacks the amount of recommendation, but there's fallback model. It's simpler, but it always gives recommendations for all users in the quantity that we need. With this fallback scenario, we can create an object that will be a combination of those two models, and automatically will give the recommendations based, there will be the union of recommendation for two baseline models. In addition to that, we have two-level scenario, two-stages scenario with the Light Auto ML library. So at the first level, we generate the objects, candidate objects. At the second stage, we arrange them using Auto ML so that we get the final recommendation. Here is the example of the code with the use of RePlay. And overall here, you can see the major stages of data processing and the working with data. We have tried our best to make an interface that is intuitively comprehensible and simple. And I believe that the titles of functions and the code are self-evident. Let me reiterate, this is open source solution that is available at GitHub, and you can easily install it with pip. Here's the command. And now I would like to hand over the screen back to Alexey. He will tell you more about how we have been applying RePlay for the recommendation, for the book recommendation project. Indeed. Dear colleagues, welcome, greetings. Greetings once more. Let me try to switch the slide. Not working yet? Oh yeah, it worked. So, colleagues from Moscow bookshop at Arbat Street requested us to build the recommendation algorithms for the books that they sell. Moskovsky Dom Knigi, Moscow House of Books. So they requested to improve their current system of recommendation. So we suggested them to use Sber Cloud so that they could load it all via the cloud. So let us see the video with the colleagues. They will tell in more detail what exactly they have been doing and how they have been using our tools. Dear colleagues, let's start the video. Yes, good day. My name is Vadim Safonov. I am the IT director for Moscow House of Books. Good day. My name is Ivan Yumashev. I'm director in charge of development of the Moscow House of Books. We want to suggest you take a look at the recommendation system that we have developed. It's very important to learn to sell via internet these days and online those goods that are sold both offline and online. So it's a very important amendment to our website. At the moment, we already have some. We did have some recommendation system, but its quality left a lot to be desired. That's why we approached it in a very serious way. And we have stopped our choice at the RePlay library. That is an open source solution that we considered to be optimal for implementation. We have consulted with our colleagues from AI lab of Sber, and they suggested to use Sber Cloud as a solution for cloud for this project. So the pilot is that something that we want to present to you right now. Let us see how it works live.
Давайте посмотрим, как это выглядит.
Let's look in some detail at how it looks like and what tasks the colleagues solved. As a matter of fact, the colleagues needed to solve not only task for recommendation, classical task for recommendation, but also some other tasks. And the first thing that you might have noted in the video, with the recommendation engine that they had previously, there were too many duplicates. For example, you open a book, some sort of book, and you see the recommendations, and instead of 10 real-life recommendations, you could get 3 or 4 similar books, and the only difference was date of release, for example, or publishing house. Of course, that's not a great recommendation algorithm, so the colleagues had to delete duplicates manually. We suggested how to automate that, and that's a very specific and exciting sort of task. The disadvantage of some sort of external engines is that it's hard to delete duplicates. 2 additional tasks that were solved for recommendation are recommendations of certain books to users, registered users, I mean, and recommendations of similar books, similar to other books. And in addition to that, in every shop there are many books that are not purchased, so we needed to solve a problem of cold start for those books that don't have any collected data, so that they would fall into the recommendations, so that all of this would work autonomously and in a more contemporary way. We needed to build the system as a service. Let us continue and take a look at how it's made. So, thanks to ML Space, that is the cloud technology of Sber Cloud, they loaded the script that was executed, and within there was a scheduler that worked according to schedule once in every 24 hours. Out of the external sources, the colleagues were putting into ML Spaces their data on a daily basis, and scheduler was taking them and launching the script. In the end, the data were returned to the MySpace S3, and colleagues were getting the data back. This sort of scheme works every single day non-stop, quite autonomously. We have taken a look at the use case. That was our first pilot, I mean. So now you may see on screen the links to documentation and repositories in GitHub. Please join to participate in the development. Our library is actively growing at the moment, and also wanted to highlight that we invite to our team people who are very keen on recommendations. So, thank you very much for your attention. Thank you. That was a beautiful presentation. We don't have any questions at the moment, so thank you very much, and wishing you the best of evening.